very lucky, and it's my pleasure to introduce Dr. Yang to give us an overview of what we can learn from neutrons about the structure in a sample, the spatial correlations in a sample. I don't know what he's actually going to tell us about, so I could keep going. But I'm pretty sure there'll be long-range order in there.
Yeah.
I'm not sure if we get to short-range order, but we're going to be looking at the correlations between entities in samples at different length scales, which is very important to a lot of the examples you heard earlier on this morning, where you need to know what your material really is first before you can go on and study it further. So with nothing else to do and no announcements, Dr. Yang, you mind?
So thanks, Jason. And I think the first time I meet Jason is at the Chaco River. I think it's about 2001, something like that. That's the last chance before I pass the PhD qualify. So it's a hard time for me and go to the Chaco River. And fortunately, the security is so tight in Chaco River. There are security guards with guns. So when you want to pass the gate to the nuclear facility, it's really hard. So most time we just do the things, just deliver sample to the Jason and check data daily. And most time I can read my book, and sometimes we try to escape to the North Bay, but Jason always warned me, do not go to the North Bay, and do not go to a very bad Chinese restaurant, right? And we have a chance to go to some restaurant to eat the chicken wings. And Jason also drive us to a beautiful place that would be wooden buildings with large glass window, and a river just crossed in front. And at the other side, the river shore is another forest. That's a very beautiful memory for me. So I thought this is just encourage the people to go to the neutron experience, because that will give you a very beautiful and sweet memories, right? Okay. So that's not the topic I want to talk about today. And this is my actual topic I want to talk about. So the topic I want to talk about is the high resolution neutron powder diffraction and the data analysis. Before the lunch, I just talked to Jason. I would like to mention to the people who want to go to the neutron scattering. That is, there are differences when you have some X-ray experiment and the neutron experiments. Most people in Taiwan, I know, they are used to compare with the data, such like JCPD database or ICSV database to their X-ray result. But it is very expensive in the neutron beam resource. In the last talk of the Jason, he mentioned us that the neutron beam would be 3 new Taiwan dollars per second. So roughly, we can calculate that you may pay, you don't need to pay. The cost of the neutron beam would be $280 per day, or 1.8 million per week. So that's a very valuable experiment data. So before you go to the neutron scatter, you need to have a good skill or good ability about the data analysis. So my name is Chong Yang. I come from Department of Physics at Chongyang Christian University. This is the outline. Today I want to have a briefing about neutron, some neutron instrument, the basic idea, how the high resolution neutron powder diffraction do. And so as I mentioned before, we need to have some basic concept of the powder diffractions. And I would like to tell you how the importance of the material we find in the powder diffractions. If you have such skill and this knowledge, you would have you can extract very very much information from your data. And then I will give some examples what can neutron powder diffraction do in your experiment. So in the first, I want to talk about hydrogen powder diffraction. And this plot already appeared 3 times today. So you will know this is very important plot. And here I just want to mention a little bit more is about when you need to reserve your crystal data, especially for the very narrow spacing. You need a neutron is much better than the X-ray because of the X-ray, the intensity will be also not only in atomic number but also in the angle. I mean, when you go to the high angle, the efficiency or intensity of X-ray would be very small. But for the neutron, as the Professor Lee said in the morning, that's because the neutron would be interacting with the nuclear. So it also have high efficiency at high angle. So when you go to the high angle, that means that this spacing is very, very small, and you can see very detailed about the spacing between atoms. So that's the one thing I want to mention more. And this is a typical configuration of the powder diffractometers. And this drawing is comes from the NIST BT1, and this is a banana detector, and they did painting in the yellow, so it looked like a banana. Okay, so the neutron was produced by the reactor and then introduced from the neutron guide, and this neutron surpassed the filter, just filtering some remove some energy you don't want it. And after the monochromator, you just choose the in certain wavelengths you need to use, and the neutron beam would be direct to the sample side. The diffraction neutron were collected by the multi-detectors. So in most powder diffraction instruments in the world, they all use the multi-detector systems. So this is the case of the echina. So echina in Chinese seems like called 针燕, the kind of animals. So you can see there's some needles look like multi-detectors. So in the echina they have 128 precision sensitive detectors, and they did not paint it in yellow, right? Okay, so this is steel banana, something like that. Okay. And this is the spec of echina. So I just want to talk about they can choose the wavelength from 1 to 3 angstrom, and the maximum beam size would be 20 by 50 millimeter, 20 by 50 millimeter. And the typical data collection time would be 2 to 3 hours. So compared with the synchrotron X-ray, that would be not so bright, because when we go to the synchrotron X-ray, the things you need to worry about is the saturation of the CCD detector. And every time when I'm a student, I go to the synchrotron, the collection data is a nightmare for me, because I always change the sample in 5 minutes or 3 minutes. But when we go to the NIST, my boss always drive me to outside and shopping, movie, and shopping, and that's beer, and lobster, and yeah, that's right, and lobster, that lobster is really good. Okay. But now we have some improvement in the echina, so we don't need 6 to 8 hours. We just only need 2 or 3 hours. And Jinwei ever tell me, if you got a lot of quantity of your sample, maybe we can cut time into an hours, right? Okay. And the sample environment is also important. So I think they provide the temperature range from 1.8 K to 1800 okay, this is degree Celsius, and the pressure, they also have some pressure upstream and magnetic upstream. So you can have various experiments in the powder diffraction bin. And before you go to neutron scattering, powder neutron diffraction, you can have some simple calculation about your experiment. So these are the calculated from the NSTO web page. If you want to resolve get a better resolution at high angle, you can simply choose the different monoparameters and the collimators. So you can before you go to the NSTO or before you write in the writing a neutron proposal, you will know if the instrument can achieve the target that you want. So these are two examples. This is about the delta D by D against the 2 theta, and this is half width at against the 2 theta. And the other thing is, when you request the bin time, how long do you need? So they also provide an calculators. This is an example. These are wrong numbers, but it's just an example. This is the case of BFO. It's a multivariate materials, and if you can just simply choose the elements you need and the quantity or the sample height in the cylinder uranium can, and if you know the packing density, you can estimate the time you need to count. So when you write in proposals, you can first calculate the time you need and write the correct number. Maybe you can provide this information. That would be easier to get your own bin time. So that's the part of the instrumentation. And the second topic I want to talk about is I'm not sure if the people here would be well known in diffraction or not, but even everybody is an expert in here, but maybe your student is not. So I think before you go to the neutron powder diffraction, you have the best, or your student have best to know such knowledges. So I would like to talk about the basic concept of powder diffraction you need to know. So this is the feature of the powder diffraction. Although this is not neutron, this is the X-ray pattern, but the feature is identical. So the intensity would be proportional to the structural factor square, and the peak position is correlated with Braggs law. So these are equations. I don't want to mention too much about this. Even I don't want to direct you the equations, but these are the basic idea and basic knowledge before you go to have some diffraction experiment. So I think this here is at least the sixth topic before you have experiment. You have better know what is this means. So the Braggs law, I think everybody knows Braggs law, and the Miller index, it is also well known by everybody, because at least if you want to compare with JCPD database, you also need to know which Miller index you need to match. And structure factor is correlated with the atom position in the crystal. And the multiplicity factor is the duplicate of each Miller plane. And the defined water factor is also a very important, but always be ignored by most people, because this is about the temperature effect, and that will cause the intensity change, relative intensity change between peaks. And the space group, most students do not realize the importance of the space group, because they will give you if the peak exists or there's symmetry in the crystal. And if you have knowledge of these 6 parts, you can determine and understand how the peak intensity growth and the peak position appear. Okay, so the Bragg law is, I think it's well known. I don't want to talk too much about this and just skip. And two theta position you can simply calculate from the Bragg law. You just need to convert the spacing from the middle index and the lattice constant. That's quite simple. So this is an example for the cubic. And the equation will be reduced to the short form. So for the simple case, if we want to calculate the spacing of the gold 111 pen, you can just start from the Bragg law, and if you know the lattice constant and the middle index, you can after some very simple mathematics, and you can get that the theta would be 19.1 degree, and the 2 theta would be 38.2 degree. So we can find the actual peak position appears at the 38.2 degree. So that's quite simple. I think all the students can do this, especially they are measuring the size-state physics or some diffraction techniques. And the structure factor is usually appears in the solid-state exam. So people always have the BCC or FCC calculations. And students, I think the students would always know how to calculate the structure factor of BCC and FCC. So this is an example for the BCC structure. So because this is quite simple, so I want to talk much about this. And this is an example. If we got the calculation about the structure factor, the intensity would be look like this, and this is the intensity, and this is 2 theta along the x-axis. For the FCC, the HK are need to all even or odd, and the intensity would be proportional to the 4f squared. And this is the BCC structure, and this more complicated are the HCD structure. So that's really important, but very simple for everybody. And shown here is the multiplicity factors. The reason of the multiplicity factors comes from the identical D spacing between each planes. For example, if you have a 0, 1, 0 plane, you also have another equal spacing of 0, minus 1, 0 plane. So the distance are identical, but you just count once in your structure factor. So you need to duplicate or multiply by the number of these identical plane. So this is another example for the 0, 1, 1 and the 1, 1, 1 plane. So the rule is you can simply multiply the factor of 2 to the n is the non-zero number in the middle index. But this rule is not it is not suitable for some structure like a monoparameter or triclinical. So if we take into consider about the multiplicity, the FCC structure would give you a different distribution of the peak intensity. So we can see if you consider with the multiplicity, the peak intensity would look like this, and this would be BCC. If you remember, the BCC have the same intensity at a different angle, but now they are different, and this is HCP. Okay, here is another very important factor called Debye water factor. The reason of the Debye water factor appear is come from, you can imagine that the atoms are not steady in the unit cell because they would be vibrate as the temperature increased. So when the atoms are vibrated, the incident neutron beam will see an effective area. It is not a pinpoint. It will becomes an if you cut into a slide, you will see an area inside the space. So when the neutron beam want to impact with these atoms, the effective area would be effective cross section would become bigger. So the unit of the Bywater factor is the unit of the area. That's the basic idea of the Bywater factor. So what's the effect about the Bywater factor? It will case the intensity would be decreased with the angle. So this is the typical shape about the decreasing of due to the Bywater factor. Of course, right here is the X-ray Debye temperature, but actually all the diffraction will give you the same feature due to the Bywater factor. And this X-ray Debye temperature would be usually used by the X-ray diffraction. They can calculate the X-ray Debye temperature, but that's very different from the Debye temperature because X-ray Debye temperature is take into account about the average vibration frequency, but not the cut-off vibration frequency. That's quite different. But you can also calculate some speed in the crystal by this method. And the other very important thing is about the space group. The space group is my student always tell me the space group is like a magic. Is quite strange because they have 4 letters and they can give you a lot of information. Yes, the space group number. This symbol have a lot of meanings. If you are well know the meaning of this symbol, you can construct a crystal structure in your mind before you really see the drawing of these structures. So what's the meaning of these symbols? So the symbols space group will always be written in the form of APQR. Here A is the type of crystal and the PQR is associated with symmetry operated along a specific axis. What does this mean? If the symbol A is represented as the crystal type, such as P means the primitive cell. That means a primitive cell is mean in a unit cell there are only one chemical formula. And the C means the base center. The base center is if you have a crystal, you can imagine that at the top and the bottom. The center will be put at the center face, top face, and the bottom face. There will be an atom put into the center. So that would be called a C symbol. And I means isotropic. You can imagine that when you sit inside a crystal, and all around you are look like the same. So that's an isotropic. So we also call the body center. And the face center is very easy. So just at 6 faces, you put the atoms inside the center of these faces. So from the first character of the space group symbol, you can know what kind of the crystal structure you have. And the PQR are the operator, the symmetry operator for the crystals, such as M is mean the mirror. So you can imagine that there is a mirror and you put the atom here, you would have another identical atom at another side. And there may be some numbers appears in the APQR, like 3 means 3-4 symmetry. If you rotate the crystal, the number 3 means you can divide it 360 degrees by 3. You can get the identical structure when you rotate the crystal. But there are some misunderstanding about the symbol is the PQR for most people they always think the PQR is correlated with A, B, and the C axis. But this is wrong. For example, in the cubic cell, the PQR are correlated with the symmetry symmetry axis along the A or A plus B plus C or A plus B. That means 001, 111, and 011 direction. So, for example, this is the space group of vanadium. The space group is called IM-3M. So the symmetry axis would be along the A axis, and the 3,4 would be along the 111, and the finally M is correlated with